So sometimes we want to know, is this population the same as this one, or are they different? Is population 1 bigger than population 2, or is population 1 smaller than population 2? Like, what is going on with these two different populations? So we would want to find a difference in their proportions to see, are they different? Are they the same? What's going on? So in that situation, we're going to use a sampling distribution for a difference of two different proportions. So we would have a simple random sample of size N1 from population 1. There would be a proportion of success of P1. Then we would go to the second population and we would take an independent simple random sample of size N2 from population 2 with a proportion of success of P2. What does the sampling distribution look like? Well, the sampling distribution looks like this with a mean of P1 minus P2. So you just take P1, subtract P2. Do we usually know the population P anymore? Nope. So what do we do if we don't know the population P? We stick hats on them, right? So P1 minus P2 would be the mean of this sampling distribution. The standard deviation, look at that fun formula. Doesn't that look good? I love that. That's so pretty. So P1 times 1 minus P1 divided by N1. Now, if you guys just look at that one little part there, that looks very similar to the standard deviation formula we've been using, but we're just adding on the next one. So even, yes, ma'am? Yes, so even though we're doing a difference between the two proportions, remember, when we combine standard deviations, we always have to add them, just like the Pythagorean theorem. You're always doing a squared plus b squared. We're always doing the standard deviation plus the standard deviation, and then take the square root of that. So even though we're doing a difference of proportion, it is a plus in the middle. That's not a typo. Now, how do I know if the shape is going to be normal? Well, here's the deal. Y'all are going to be so excited about this. You are going to get the opportunity to check N1 times P hat 1, N1 times 1 minus P hat 1, N2 P hat 2, N2 P hat 2. That's like R2D2's little brother. Thank you for laughing. I appreciate it. N2 1 minus P hat 2. Okay, so you guys, not only are we doing it twice with the first two there, we got to do 4 checks. And what do all of these have to be greater than or equal to? All have to be greater than or equal to 10. Yes. So this is just like we've been doing, you guys, but we don't get to do everything once. We get to do everything twice. Doesn't that sound fun?
I am so sorry. I'm so confused.
I was like, did someone find that
R2D2
R2D2
really funny?
I know, I was too. I was like,
One R2D2.
I was like, that R2D2 joke just went next level right there. I love that. All right, so, yeah, exactly. All of these have to be greater than or equal to 10. All right, cool. Now I have really good news for you guys. Formula chart, okay? So these 2 lines are on your formula chart. Obviously, we've seen these before, right? So that was for one proportion. Here's 2 proportions. So they're right here on your formula chart. Here's your mean. Here's your standard deviation. Okay. Now, what about the test statistic? Ugh. I know. I hate this board. It's the dumbest smart board I've ever had in my life. All right, so there we go. The Z test statistic for a difference in proportions. Here it is. We're going to take P hat 1 and subtract P hat 2. That's on the top of the fraction. Now that's really good news because that's basically the mean of the distribution. I'm just putting hats on it because I don't know P. So there you go. P hat 1 over P hat 2. P hat 1 minus P hat 2. Then I'm going to take that big, giant standard error formula right here, and that goes on the bottom. P hat 1, 1 minus P hat 1 over N1 plus P hat 2, 1 minus P hat 2 over N2. This is how you get the z-test statistic. Doesn't that look like a fun time?
Yeah.
Who wants to do that by hand every time?
That's what
Nobody? Come on, you guys. It's 2/22/22 today. It's like Tuesday.
it's the tutus.
It's the Tuesday day. We should want to do math all day, every day, and fill. No, I don't even want to do this, y'all. Like, where are you going to get this actually from? Thank you, calculator. Everybody look at your calculator and say thank you.
Thank you.
All right, cool. All right, last thing before we do our example here is how do we write these hypotheses? So these are going to be slightly different than what you guys are used to. Now, the null hypothesis is always that P1 is going to equal P2. Now, I can write that in a slightly different way based on the fact that I'm doing a difference of proportions. So I can write it as P1 minus P2 is equal to 0. How do these things, how are these equivalent? Those look different. How are they equivalent though?
Because if you subtract the same number, you get 0.
Yeah. So if I subtract P2 over here, I get P1 minus P2 equals like nothing. So that would be P1 minus P2 equals 0. Those are equivalent. Those are always your null hypotheses. Okay? For your alternative, it depends on what you're thinking. Do you think that P1 is greater than P2? This is your alternative. Do you think that P1 is less than P2? Or do you think that P1, what's the third option?
Not equal to.
Perfect. Not equal to P2. Perfect. Now, that's one way that these might look. Okay? But I can make them look like this as well with the 0. Okay? So, what would this one look like as the alternative? What would it say? Yes, go. Come on, girl. You got this.
P1 minus P2 is going to be greater than 0.
Perfect. Absolutely. P1 minus P2 is greater than 0. Perfect. All right, the second one. What would the second one look like?
P1 minus P2 is less than 0.
Perfect. P1 minus P2 is less than 0. And what would this one, last one look like?
P1 minus P2 is
Awesome. Okay, so just a quick reminder, you will not get a p-hat in your hypotheses. These are always p's, not p-hats, nothing like that, okay? And you could write them either way. These are equivalent. It doesn't matter which way you write it. I just want to caution you guys on your multiple choice stuff. You could see them either way, so you might want to just get comfortable seeing them both of these ways. All right, guys, what questions do you guys have about the hypothesis statements? Perfect. All right, let's look at your blue sheet real quick. Back side of your blue sheet. All right, so we've got our 2 proportion z-test. This is called a 2-prop z-test instead of a 1-prop z-test. Why do you think there's a 2 instead of a 1?
because you're dealing with 2 p's.
I got 2 different populations, 2 proportions happening. Yes, very good. Notice that it looks very similar to what we've been doing. State, plan, do, conclude. Oh, wait, what are those 4 steps again?
State, plan, do, conclude.
Okay, cool. And so we will test at alpha equals blah, 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 blah. We've got our plan. Oh, wow. You guys, look at the plan. Random. Not only do we get to check the SRS for the first one, we get to check it for the second one. And then our 10% condition, we get to check it for the first one and the second one. Doesn't this look so fun?
So much more work.
So much more work. Is this difficult?
No.
Not even a little. Is it tedious?
Yes.
100%, yes. Okay? But that's just the nature of being a statistician. We're just tedious people. Okay. Let's see what we got going on here. The Pew Research Center recently selected a random sample of 269 18 to 29-year-olds and found that 59% of them use Instagram. Are you guys using Instagram? Yeah? Do you think that is low?
Yes.
That's probably a little low. We'll go with it, though, you know. It's Pew. They know everything. A separate random sample of 401 30 to 49-year-olds found that 31% of them use Instagram. Do these data give convincing evidence that a greater proportion of 18 to 29-year-olds use Instagram than 30 to 49-year-olds at a 5% significance level? You guys, look at the data. Are the 18 to 29-year-olds using Instagram more than 30 to 49-year-olds do?
Yes.
Obviously, yes, it very much so. So, do you think we're going to be able to reject the null hypothesis of them being equal to each other? Probably. We'll see, though. We want to make sure that this was a statistically significant difference, not just sampling variability. Okay, what do we start with? State. State. We will test. This is so exciting. We will test at alpha equals. What's alpha equal?
0.05.
Yeah. So this one it told us in the problem, but it's the same one we always use. All right. Null and alternative hypothesis. I want you guys to write them down. Let's see if you can come up with them. So write down what you think they would be. Be careful with that last sentence, though. Null and alternative hypothesis. What do you think they are? Yes, ma'am. Make sure you check out that last sentence there.
I don't know if it's like includes or the last sentence sounded like.
So these data give convincing evidence that a greater proportion of 18 to 29.
So the P1 is
There you go. There you go. Okay, let's see if you guys got it. What do you think the null hypothesis is? Well, I mean, it's the same every time. Yeah. Okay, so we got that one. Y'all have a fantastic day.
Yeah, thanks for really stressing me out.
Hey, don't be stressed. P1 equals P2, okay? What about the alternative? What do you guys think? You think it's a not equal to?
Yeah, greater than.
You think it's a greater than?
P1 is greater than P2. Yeah, P1 is greater than.
Oh, greater part.
All right, P1 is greater than P2. Now, I want to caution you guys. That just kind of actually depends on what you now define as P1 and P2. Because right now, P1 and P2 are not defined. You have to define them. So make sure that when you define them, that you define them correctly. So P1 is going to be the true proportion for what? For who?
18.
Yeah, true proportion of 18 to 29-year-olds on Instagram. And P2 would be the true proportion of 30 to 49-year-olds on Instagram. Now then, that is what the problem is saying. Okay, and then just as a reminder, you could see this written as P1 minus P2 equals 0, or P1 minus P2 is greater than 0. So you could see it either way if you were looking at a multiple choice question or something that was already written out for you or whatever. But there's your null and alternative hypotheses. Okay, what's next? We get to plan, and you guys, we get to plan everything not once but twice. Wow, this is so exciting. Random. We have an SRS of 269 18 to 29-year-olds. And we have an SRS of 401 30 to 49-year-olds. Yay. We have ourselves 2 SRSs. Woohoo! 10%. We need to make sure 10 times our first sample is less than the population of the first. So 10 times 269. Do you think that that is less than the population of 18 to 29-year-olds? Probably. I mean, I think there's more than 2,690 18 to 29-year-olds in the world. And then we're going to check that 10 times the second sample size is less than the second population. So 10 times 401 has to be less than the population of 30 to 49-year-olds, which again, I'm fairly confident would be true. And now what do we get to do? Normal. And oh boy, do we. We get to do all kinds of normal. We need to check N1 times P hat 1 has to be greater than or equal to 10. All right, N1 was 269. That was our sample size for the first sample. P hat 1, this was the proportion in the sample that used Instagram. What was the proportion in the sample that used Instagram for the first population? 0.59. Okay. I do not know what 269 times 0.59 is, but you have calculators. And I will tell you this. You should round them to the nearest integer, like regular old rounding. So when you do these, don't use decimals. Make sure you're using integers. So what is 269 times 59% as an integer, the nearest integer? 159. All right, so that one's good. Now we're going to check N1 P hat, or I'm sorry, N1 times 1 minus P hat 1. So 269 times 0.41. 269 times the complement here. And what do we get? 110. That one's bigger than 10. Okay, cool. We're rocking and rolling. N2 P hat 2 has to be greater than or equal to 10. N2 was 401. P hat 2 was 0.31. 31% of 401. 124. Okay, that one's good. And the last one. 277. We're golden. We have ourselves a normal distribution. I want to remind you guys real quick what these numbers also mean. 159 is the number of successes in the first sample. That's the number of people who use Instagram in the first sample. That's the number of successes. 110 is the number of failures in the first sample. That's the number that don't use Instagram in the first sample. 124, that's the number of successes in the second sample. And 277 is the number of failures in the second sample. Do you guys have any questions about state or plan or any of this so far? Again, this is not really hard. This is just tedious. And now we get to go to the calculator. Let's do it. Do. We're going to use a 2-prop Z test. Please make sure you are using a 2-prop Z test. If you use 1, you will not get anywhere close to the right answer. When you go to a 2-prop z-test, it's going to ask you for x1. That is your number of successes in the first sample. And you already found that in the normal when you did N1 p hat 1. So what was the number of successes in the first population? 159. N1 is our number of in our sample, and that was 269, right? X2. That's the number of successes in our second population, which we calculated when we did N2 p hat 2. And what was that? 124. And our N2, 401. And then you're going to see, how does P1 relate to P2? That's based on your alternative hypothesis. And then you calculate. You're going to get your z-test statistic and your p-value. Remember, your p-value in your calculator just says p, which is really annoying because it's not a p, it's a p-value. But me and T.I., we haven't come to terms yet. Oh my gosh, you guys. You have a pretty interesting z-test statistic, don't you? What is your z-test statistic, ladies and gentlemen?
7.24.
Holy cannoli. Here's what this means, you guys. In the middle of the distribution is where P1 equals P2. Our difference is 7.24 standard units above what it would be if they were the same. If they were using Instagram at the same rate. We are 7.24 standard units above them being the same. And look at your p-value. Yeah. What is that p-value?
2.25. To the
Times 10 to the negative 13th. You guys, don't miss that. This is a teeny tiny number because the probability of us getting a difference as extreme or more extreme than what we got just because of sampling variability is pretty much zero. The chance that this was a sampling variability difference is pretty much zero. So what does that mean? Well, that means that there's a big difference between 18 to 29-year-olds using Instagram and 30 to 49-year-olds using Instagram. Are you shocked?
No.
Not at all. Yes, ma'am.
Why is N1 greater than P2?
So in the very last sentence of the question, it says, do we have convincing evidence that the proportion is greater for the 18 to 29-year-olds? Yep. Okay, so we can now conclude. Our p-value, which is like super duper small, is super low compared to our alpha value. And what do we do when our p-value is low? You got it. This is an easy rejection right here. We have really convincing evidence here. So there is convincing evidence that P1 is greater than P2. Now we're going to go ahead and say what that means. We have convincing evidence of our alternative, and we're going to go ahead and say what that means. That means that 18 to 29-year-olds use Instagram more than 30 to 49-year-olds. Now, I hesitate to even ask this, but I'm going to anyway. Could we have made an error? I mean, maybe. Theoretically speaking. If there was a possibility of an error being made, what would it be?
Type 1.
a type 1 because we rejected the null hypothesis, so we could have made a type 1 error. Is it likely that we made a type 1 error? Not really. Okay. It's pretty clear here that there's a big difference. That is a 2-prop z-test. What questions do y'all have?
My hand hurts.
I know. Again, not difficult, very tedious. All right, cool.